There it goes. All right, so we that participants window, and one more thing. Sorry for the brief delay. When I start sharing my screen, it switches it all around. So, all right, there's the chat. Okay, so we are going to finish boundary layer theory today. Let's just review where we're at real quick. So we've been talking about external flows at high Reynolds numbers, okay? And we said we're going to focus on the momentum problem because it's canonical. And the first thing we did was non-dimensionalize the Navier-Stokes equation, which I think Brian, he doesn't look like he's here, but Brian guessed we do, all right? And we saw that we got a 1 over the Reynolds number in front of the viscous term. And that meant that at order 0, this is a small number at high Reynolds number, and at order 0, that term drops out and we get Euler's equation, which was a singular perturbation problem. And so that meant we were going to have two regions, an inner region and an outer region. And the outer region, we saw that we were going to solve inviscid flow or irrotational flow problem. It often ends up as an irrotational flow problem, which was governed by Laplace equation. And the inner region, we said we were going to have to rescale. So we finished that rescaling last time. So we talked about Laplace equation, and then the rescaling gives us what are called the boundary layer equations. So to rescale, we said we were going to zoom in and look at just a flat plate. And we said that the geometry of the outer region wasn't really going to affect these equations much anyway. So we could just think about it like a flat plate. And we rescaled the velocity by some new velocity v and y by some new length scale delta. And when we did the continuity equation, we found v. V was related to delta over L multiplied by u. And then when we did the x momentum equation, we found delta. And that took a little bit more algebra. That's what we took a bunch of time last time to do. And we found that delta over L went like the Reynolds number to the minus 1/2, which was epsilon to the 1/2, our small number to the 1/2. And we did that so that we didn't lose all of our viscous terms. So now we keep a viscous term dvx dy, so how the velocity is changing in the y direction. But the dvx dx term, there was no saving that one. It was gone, okay? And we end up with the boundary layer equations, which have the convection terms on the left-hand side, the pressure term, and then the viscous term for the change in the y direction, all right? And we put that back with units. And there were a couple of things we got out of this. So we got the boundary layer equations. We also got what delta was, which is the boundary layer thickness. So that tells us that the boundary layer thickness changes as a function of distance, that distance L, and that's nice to know. It helps us know that it's, what the size of our inner region versus outer region is going to be. And so that was valuable. But we only knew it to within a constant, and we'll have to solve the whole equation, not just do some scaling arguments to get more than just that. And then we sort of stepped back and said, now we're going to be on part C, which is how do we do the full solution to this boundary layer problem. So we kind of reviewed, we said there was an outer part and an inner part. And in the outer part, again, we had Laplace equation with the outer boundary condition. And in the inner part, we have the boundary layer equation. And then we knew we have to find the pressure somehow. We have the pressure derivative in y was 0 from the y momentum equation. And from the continuity equation, we could get the Vy that plugs in here. And we have the inner boundary condition here. So to solve a boundary layer problem, you have to solve the outer problem first using the outer boundary condition, and then find this dp dx term, which you get from Euler's equation. Then you solve the boundary layer equations in the inner region, and then you use the inner boundary condition and matching conditions to find the constants for the boundary layer equation, okay? So that's a whole mouthful. All right, but that's what we've been doing. That's what we've been working towards, is this Blasius solution to the boundary layer equation. And so we said, okay, we're going to go look at the Blasius solution for a flat plate. And what's going to matter at the flat plate is it's going to fix this thing for the inside, right? So we said the outer solution was trivial. It was just u over the flat plate far away for in the Vx direction, the Vy direction 0. we could find the pressure gradients, they were 0. So that made our life easier. And we got a simplified boundary layer equations when dp dx was 0 here, where now we only have the convection terms and the viscous term on this side. And we said this is a nonlinear PDE, but we were going to try and solve it anyway. And we said, how might we solve it? Well, Blasius noticed that this is a semi-infinite problem, so he tried a similarity solution. He said, let's take y and divide it by some function of x. And he said, let's divide it by the boundary layer thickness. And maybe if we rescale y by the boundary layer thickness, we'll be able to do something and do a combination of variables, right? And so that's what he said we're going to do, is try to turn this PDE back into an ODE, which is only a function of eta. And we took our boundary layer thickness and we turned the L into an X, and we threw in a 2 here for our constant, which I said we could get at the end if we wanted, but I'm doing it at the beginning, so we save ourselves a lot of square roots of 2 all over the place. Okay, so we got to there in the boundary layer equations, and then we said we needed to do a quick aside to talk about the fact that we had Vx's and Vy's in here, and we also had this continuity equation bit with Vy as the integral of dVx dx dy. We said that's real pain to play around with, so we were going to use a trick that's really common in fluid mechanics, which is to use what's called a stream function. And a stream function is this kind of weirdly defined object that, if we have time today, I can talk a little bit more about the Helmholtz theorem. I went and did a little background of that in case we have a little extra time. But basically we can define the velocity in terms of this other thing, which is a cross product of something, all right? And it ends up defining the velocity as the derivative of the stream function with respect to y, and the velocity in the x direction. The velocity in the y direction is the derivative of the stream function with respect to x. And this seems like it's just making our life more complicated, but in actuality, this stream function, if we plug it in, it automatically satisfies the continuity equation. And so then we only have to solve for one thing, a stream function, instead of two things, a Vx and a Vy. And so that makes our life easier, actually, because now we can collapse this PDE. It would still be a PDE, but a PDE in only one variable instead of a PDE in two variables with two equations, right? So basically, before we had two equations and two unknowns, and this collapses it down to be one equation, one unknown, because we can use the stream function. So that makes our life a little bit easier, okay? So that was where we got to last time. And so I'll just pause here real quick and make sure we understand that, if there's any questions before I dive into the Blasius solution. Okay, so everyone's on board with that. We good, Zach? Make him find his mute button.
Yes.
Okay, picked on him. Okay, here we go. So that's the end of the aside. That's what I'm going to call right there. Okay, so now we want to go back and we want to do the stream function, and we're going to simultaneously do this. We're going to simultaneously do stream function and rescaling. It's actually not too hard to turn this guy back into a stream function. You just take these derivatives and plug them into this and the continuity equation, and it gives you something pretty easy, but then you still have to do this rescaling, and it's easier kind of to just do them at once. So remember, we're going to have eta is going to equal y over delta, which is going to be the same thing as y divided by the square root of 2 nu x divided by u. And then we're also going to make a substitution. We're going to say that Vx divided by u is going to equal some new function df d eta. And what is f? F here is going to be related to the stream function. So the stream function is minus u delta f of eta. Okay, so in other words, if we go back and look at this df d eta right here, this is like saying d psi dy is equal to Vx, okay? And so we're just f is just a dimensionless stream function. So the stream function is going to have kind of funky units. It's going to have the units of velocity times, or let's see, velocity times a length. So because you have to divide by length to get a velocity out. So it's got units of a velocity times length. So we plug that in and we get out Vx over u, and we make it negative just by convention. So this is what Blasius did, is he made it negative. Okay, I don't think there's any particular reason. So f here is a dimensionless stream function. Okay, so new page. Okay, so now we've got this Vx over u, and what we have to do is go plug these things back into our original equation up here. Okay, we just need to plug these definitions in. So for example, I'll rewrite the equation so we can see it. So plug these definitions into the following. Vx is multiplied by dvx dx plus vy multiplied by dvx dy is equal to nu times second derivative of Vx with respect to y squared. Okay, so some of them are really obvious, right? So the first one is, Vx is equal to u times, and I'm going to call this df d eta, I'm going to call that f prime. Okay, I'm going to call f double prime, the second derivative of f with respect to eta squared, etc. Okay, so the first one, Vx is u times f prime. That's pretty easy. That will get plugged in right there. But then we need to have the derivative of Vx with respect to x. And that gets a little more complicated. So I'll do one of these out, and then I'm just going to tell you the rest. So if we have dvx dx, this is going to be the x derivative, and then we have to plug in u f prime. So u f prime. Well, f prime is a derivative with respect to eta, but we don't really know how to do that with the derivative here. We want something that's only in terms of etas. We want to get rid of this guy, right? We want only in terms of dd etas. So to do that, we're going to need to use a chain rule. Right? So the chain rule says that, and u I can pull out here. So this chain rule says that ddx of f prime is the same thing as u d, let's see, I want d eta dx d eta of f prime, right? Did I do that right? I think so. So this is my chain rule. I'm expanding that x derivative to be the eta derivative, right? So I do d eta dx d eta. And so now this d eta of f prime, well, that's just, d eta of df d eta. That's the second derivative of f with respect to eta, or f double prime. Okay, but then I need this derivative here. What's d eta dx? Well, I have eta up here. I said eta was equal to y over the square root of 2 nu x over u. So that's what I need to take the derivative of. D dx of y divided by the square root of 2 nu x divided by u. So let's see, the y comes out, and I'm going to have the square root, let's say I'm going to have 2 nu x over u to the minus, 3/2, and then multiply by 2 nu divided by a u. Is that right? Feel like something's wrong there. Depends on how I treat it. Let's see. I think I need that in
need a negative sign.
And a negative sign. Redo it like this. If I do that whole thing, I need to multiply by the inside, right? So I need to do 2 nu over u. And I need minus y. And do I need a 1/2? Why am I failing at this?
Yeah, you're going to want a negative 1/2 in front.
I need a 1/2, right?
And I think it's u over 2 nu. Instead of 2 nu over u on the outside.
Don't I? Let's see. If I do this to the minus 1/2, the minus 1/2 comes
down. Oh,
no,
I'm sorry. I'm mistaken.
This stays like this, right?
Yep, you're correct.
Okay. Yeah, sorry, I got confused. Okay, so, oops, erase. There's my eraser. Okay, so we can rewrite this a little bit nicer. This will be a, we can write a y over delta to the 1/2 multiplied by, and then this should be another delta to the minus 1 multiplied by nu over u, because the 1/2 and the 2 cancel. And what I've just done is take this 2 nu x over u, that's delta to the minus 3/2. So I've just split that up. Well, y over delta to the 1/2, or no, not delta to the 1/2. All right, I can't skip the step. Sorry, I gotta slow down a little bit. Delta is equal to 2 nu x over u to the 1/2, right? So this is a delta to the minus 3. So this should be equal to minus y delta to the minus 3 nu over u. Okay, and then y over delta is a eta. So this is eta delta to the minus 2 nu over u, because eta is equal to y over delta. Okay, so now I have my, you can see why this is a pain. dvx dx is equal to minus eta delta to the minus 2 nu over u. And let me make sure I did that right. Minus eta nu. Oh, and then I forgot this u out here. So that was just that part there. So I need to multiply by u, and then I forgot the f double prime that we had at the end. So this is minus eta delta to the minus 2 nu f double prime. Okay, that's right. Okay, so you can see how this goes. I'm just going to tell you the other ones, but I wanted to do one out so that we could kind of see what happens. But you basically do a chain rule, and you have to go through and expand all of these, deltas and do all the derivatives, and then, to collapse it back down, you can rewrite it in terms of deltas and etas. That makes your life a little easier. Okay, so I'll put a box around this one. Vx up here is u f double or f prime. Down here we've got dvx dx is this one, minus eta over delta squared nu f double prime. Okay, and then the other ones that we've got, we have vy is going to equal nu over delta multiplied by eta f prime minus f. Okay, this one, if you want to work it out, this one you need to use integration by parts. Okay, so that one is a little bit of a pain to do that. So dvx dy is equal to u f double prime divided by delta. And then the second derivative of vx with respect to y squared is equal to u over delta squared f double prime. Okay, so those are the remaining pieces when you do the combination of variables. Any questions about how we, in principle, got those? Obviously, I didn't do all the details out here. Okay, so now we can take those guys and plug them back in to our original equation. We just need, oh, this one right here. We just need each of those terms, that term, that term, that term, that term, that term. We had to find all 5 terms by substitution so we can plug them in. So let's do that. So the first one was the Vx, that was u f prime. So that was Vx right there, which goes right into that spot. The next one we need was dvx dx, which we found laboriously, right? Which is minus eta delta to the minus 2 nu f double prime. That was dvx dx. Plus, then we had vy, so that would be nu over delta eta f prime minus f multiplied by dvx dy, which is that part, which is u f double prime divided by delta. And all of that was equal to nu times this, u divided by delta squared f double prime. Okay, so that's the boundary layer equation rescaled and written with a stream function, a dimensionless stream function for that. Okay, so let's see what simplifies. So we can notice, let's see, what cancels here? Some stuff, okay. Look at this here. This term right here is minus eta u divided by delta squared, minus eta u divided by delta squared. I also have a nu there, and it has f prime, f double prime, right? F prime, f double prime. This one is a nu. I have a delta squared in the bottom, a u on the top, and there's 2 terms, right? There's an eta f prime, f double prime minus f double prime. See that? Equals nu u over delta squared. And then did I say, oh, this one up here. I missed something. Okay, up here when I said dvx, the second derivative of x with respect to y squared, this should be a triple prime. Sorry about that. So all these ones that had derivatives, they become double primes. This one with a second derivative becomes a triple prime. I just noticed I left that one off. Oh, this one here. That guy right there, which gets plugged in right there. Okay, sorry about the confusion on that. So this now should be f triple prime on the right hand side. Okay, so look at this. This term right here and that term right there are the same but opposite sides. I've got eta u nu over delta squared, eta nu u over delta squared, f prime, f double prime. So those 2 guys cancel. Okay, so now I have nu u over delta squared multiplied minus sign up front, f double prime is equal to nu u over delta squared f triple prime. And look, the prefactors on these are the same. Nu u over delta squared, nu u over delta squared. I'll move all that, and all I get is f triple prime plus f double prime is equal to 0. And that's the final thing. That's called Blasius equation. Okay, so that's what we solved for the inner thing. Okay, and how do we go backwards? Well, we go back to find Vx by using this equation right here, right? We can find Vx by taking u f prime. So if we can find f prime, then we can find Vx. and we can find Vy by this equation right here. So we can get Vx and Vy as we want that way. Okay, so then the last thing that we need to solve this is we need boundary conditions. Okay, so Vx at 0 is equal to 0. That's no slip boundary condition on our surface. Well, we know what Vx is. We said Vx here was equal to f prime times u. So if Vx is 0, f prime has to equal 0. So that boundary condition becomes f prime at 0 has to equal 0. That's our inner boundary condition. We also need a boundary condition for y. So Vy at 0 is also 0. This is called a no penetration condition. That should make sense, right? Like I can't have Vy's at the boundary, otherwise I'd have fluid flowing into the wall. Okay. And if you look up here for Vy, oh, where did Vy go? Vy is right here. If Vy is 0, that means that this side has to equal 0. And I just said f prime has to equal 0. So that means, all this other stuff doesn't matter and f has to be 0, right? Because if that part's 0, this could be whatever. That means f has to equal 0. So this condition says that f at 0 has to equal 0. Okay. And then the last thing I need is a matching condition. So those are the two, inner boundary conditions. Then I need a matching condition to match the outer solution. And what that says is that Vx at infinity should approach u, right? Which is the solution, which is the outer solution. And that's trivial solution. So I don't have to worry about doing the whole thing where I did the Taylor expansion or whatever, because I know the outer solution just has to be u. So Vx I already found, that's going to be f prime. And so remember that Vx is u f prime. So that means that u f prime at infinity has to equal u, or in other words, f prime at infinity has to equal 1. That's my last condition, is the matching condition there. Okay, so now we have, so what do we have here? This is a well-posed ODE, but it's nonlinear because we've got this f prime multiplication, or f double prime multiplication going on. Okay, so we can't solve it by hand. We're going to have to use numerical solutions to solve this. To solve. Okay, so Blasius did this. He came up with these tables. So you might see this table in your book of the Blasius solution, and they'll have like eta. Ooh, that's terrible, eta. They'll have eta, and then they'll have f and f prime, whatever. Okay, and they'll have this table where they came up with the solution. So I hate looking up numerical things in tables. So I just wrote my own numerical solution because I'm weird like that. And so let me share that with you. But maybe I'll pause for a second and take any questions if you have any about this while this is getting pulled up. All right, stop that share. Share this other screen. All right, can you all see? This might be a little bit small. Let's see if I can zoom in a little. Can you all see the Jupyter notebook that I have here?
Yes.
Okay. Thank you. So what I just told you was that the Blasius solution had this form, and these are the boundary conditions. So to solve this numerically, This is just like an ODE problem. It's what's hard about this numerically is this boundary condition right here, this f prime at infinity. Because how do you solve something numerically when you want to know f prime at infinity? So I use what's called a shooting method, which is where you solve it as if it's a ODE, where all of these boundary conditions are at 0. So instead of using uh, f at 0 and f prime at infinity, I use f prime and f double prime. And then I make it a nonlinear system where I solve for what the boundary condition on f double prime should be to satisfy this condition. So I'll show you where that is later. But so what I do, just like any ODE, when you have something that's in these, high dimensional ODE, you define a set of variables to decouple or to for each derivative. So that I define z0 as f, z1 as f prime, z2 as f double prime. And if you plug those in, you're going to get that the derivative of z0 with respect to eta is z1. Well, that makes sense. That's just this equation right there. The derivative of z1 with respect to eta is z2. That's just that equation right there. And then dz2 d eta should equal minus z0 z2. That's that equation right there. So this is the third derivative, is the derivative of z2 is equal to minus z0 f times z2, which is the second derivative out there. Okay, and so now I have a boundary condition for z0 and z1, but I don't have a boundary condition for z2. So instead, I just assume I know that z2 is equal to some constant. Okay, and then I'm going to solve that for what that constant should be to satisfy the condition that z1 at infinity goes to 0. Okay, so let me run this. Okay, so here's the code to do that. I've got equation 0, equation 1, equation 2. This is my right-hand side of a differential equation, okay? And what I'm going to do down here is inside solve Blasius is I do the solve IVP function, which solves an initial value problem. So I give it my initial conditions here, 0, 0, C, and C is this constant that I don't know, okay? And then eta, I have to have eta, I have to pick some range of eta. That's the other thing. So I pick eta to go all the way out to 8. Who knows, maybe it needs to go to 100, but I say 8 is enough. And then I define this other function that wraps around solve Blasius, which I call shoot, which has this constant c, which is the unknown part I don't know to the boundary condition, right? And then I use an fsolve for that shoot function. So basically it solves the differential equation lots and lots of times until it finds what the right value for c is, okay? So I can run that, okay, and plot it. And this is what we get. So f is this blue line here. I divided by 6 so it would fit on the same thing. I don't know that that means a whole lot to stare at it, but that's what f looks like. F prime is this guy here, or f prime is the green one, and you can see f prime goes and asymptotes at 1, which is what I wanted to show. And then f double prime is this curve that drops here and goes to 0. Okay, so now what I can do is take that solution and I can make a plot of space. So I can go back and plot Vx, Vy, and delta for given Reynolds number, and I can make a plot of what the boundary layer looks like. And so this is what the plot looks like here. I mean, it's pretty cool. So you can see I've got the outer solution out here, the inner solution in here. This red line is the size of the boundary layer. And you can see that down here, I satisfy no slip. And then I gradually grow until I reach at infinity the right Vx and Vy. Okay. And so that's the full solution of the Blasius, sort of condition. Okay, so I think that's pretty cool to see it all the way done out. I don't know, maybe you guys think that's really boring, but I think that's pretty neat. So any questions about this? I don't expect you, for example, to be able to know how to do a shooting method or whatever, but if you take Dr. Lignell's numerical methods class, you'll learn about shooting methods, I'm sure. I think that's why I learned it. I took Dr. Lignell's very first numerical methods class when he taught it when he was here. It was his brand new professor. That was his first class he taught. That was pretty fun. That That I really like that class. So I highly recommend that class. Any questions about this, about the boundary layer stuff? See Mark grinning at me. What you grinning at me about, Mark?
It's because you assumed that infinity is equal to 8.
Ah,
And I just think that's funny.
so yeah, I turned infinity on its side. No, yeah, I think probably what I did there was just test, right? So you can see numerically, I could probably get away with it by like 4 or 5, right? So the bigger I make that infinity, like that'll change this value of the shooting method. So we can kind of play with that. That'll be kind of interesting to see. So let's suppose I assume that eta, where'd it go? Let's suppose I assume it's 6 instead. When I solve that, that barely changed this. Let's see, 0.4695. I don't remember what exactly it was before to 4 decimal places. Let's try it with 8 and see if it's any different. 4695 still. So it really didn't matter, 6, 8. If I make it something too short, like let's make it 3, now that tells me C is 0.49. And when I plot it, you can see I'm making it be 1 at 3, right? So what I really needed to do was just play around with this enough to find out where it should go. And then when I do that, I get 4.4695. So that's where I got the 8 from, just to make the picture pretty enough. I'm assuming that's what I did.
Yeah, it's just when I took Dr. Lignell's class, I remember him saying one day that assume infinity is equal to 13.
There you go.
I thought that was funny.
Well, you should write him an email and say, today Dr. Tree told me that I could assume infinity was 8. And he told me I could do that just because I can flip it. And that was fun. So that was good for him. So, all right. Okay, so this is the end of the boundary layer equation stuff. I think like what I did with the boundary layer equations is an example of what would be like a great project. Like I don't want to say that's the standard you have to do, but something like that where you you have this problem, you investigate it, you can do the derivation out, and at the end you can present something like like these plots, right? Like that's this would be like the one, like the 2 plots you'd show in your project. That would be like I did the derivation, here's the plot at the end. That something like that would be an awesome an awesome thing to see. So many of you have talked to me about things like this. So if I've already talked to you, like, and you told me what you're going to do, like I'm not trying to tell you you have to switch now. I'm just trying to give a flavor for maybe the kind of plot you might see at the end, and see how that works out. Okay, so we've got just 4 minutes left, and there's a whole bunch of other things I could say. I think I've said most of them. I'll say one last thing just sort of as a comment. So my last part, I'll stop this share here and I'll put up a couple of comments about this Blasius solution. I'm going to share this one. So add a page here. All right, can you see this? It's showing something funky on my screen. If I write over here, can you see it?
Yeah, we can see on both sides.
All right, my screen, like when I zoomed into this, it shows like only half of my screen is sharing. So for some reason, Zoom doesn't like this. Okay, so we've talked about what we did, right? So we solved flat plate boundary layer equation. I guess boundary layer problem is what I want to say. Okay, if you do a not flat plate, like that would be a fine project to do. Suppose you did a cylinder, it would look very similar, right? But you'd still have a Blasius-like equation, but now you would have a dpdx term that would come in there. And you'll see at high enough Reynolds numbers that dpdx does funky things. It goes negative, and that's where you have a separation point. So you can use that to find the separation point. which is pretty interesting that you can do that with the theory. It's kind of fun stuff. Okay. Notice that these are all laminar boundary layers. Okay, so we can do lots of cool stuff, but we can only find out about the laminar behavior so you can find the separation point for the laminar boundary layers, but it's a little bit iffy, right? Because there's turbulence that matters. Okay, and you remember we talked about this one of the first days in fluids. If you took fluids from me, I showed these pictures of spheres and flow over spheres, and then we learn about turbulent boundary layers. And if you have too high of a Reynolds number in the boundary layer, it trips to turbulent, right? And all of those things are beyond this analysis, right? This analysis is only for laminar boundary layer problems. It's pretty powerful, but it's only for laminar boundary layer problems. Okay. The last thing I wanted to say is that there is another way to solve these problems. But it's an approximate solution. Okay, because as you can imagine, it's pretty annoying to have to numerically solve for F, right? What you'd really like to write at the end is you'd really like to have an explicit solution, right? Where you can say Vx equals something and Vy equals something, okay? This approximate solution, it goes by the name of von Karman solution, okay? And basically what you do, we don't have time to go over it, but basically you write a set of integral equations. So you integrate the momentum equation, okay? And you satisfy the momentum equation in the integral, but you don't necessarily satisfy it everywhere. So you sort of satisfy the total conservation of momentum over the boundary layer, but not at any point. So that's not really right, but it's close. But you can use it to get explicit solutions. And so you'll see these. Typically, they are written as follows. So they're written as Vx over U is equal to this function phi of eta, which is equal to 3/2 eta minus 1/2 eta cubed, or alternatively Vx over U is equal to 3/2 y over delta minus 1/2 y over delta cubed. And there's a slightly different delta of x in this case. It has a different prefactor. So instead of the square root of 2, it has the square root of 280 divided by 13. Okay, that'll be on the final. Just kidding, right? Nu x over u to the 1/2. Okay, so the same bit out here, but different, different constant. Okay, and that again comes because it's approximate. So, and you'll see these are in your book. They talk about them quite a bit, and they're convenient, right? Because now you don't have to do this whole numerical solution that you just saw me do. You can just write down that equation, right, instead of doing the numerics. Okay, so that's all I'll say about that. That's the end. That's the end of all the new transport stuff I'm going to throw at you. So thanks for listening. Please fill out the survey. So we have some stuff to talk about on Monday to review for your qualifier. And please contact me if you need help on your project. Okay, I want to help you be successful, help you get it done. I want you to get a good grade. So, any other questions? All right. Thanks. Thanks for listening, everybody. Have a great day.
Thank you.
Thank
you.
Dr. Tree, do you have any office hours before Tuesday?
I guess I don't have formal office hours, but I'm happy to just chat with you.
Okay, so I haven't gotten too far on the project